A very good morning, my dear students. Myself, Dr. Rupi Dir, is welcoming you again in this series of lectures on group theory. In today's lecture, we will discuss all about point groups, and in the end of the lecture, I will discuss some questions based upon point group from CSIR NET and GATE point of view. Hope you will enjoy the lecture. Let's start. Well, in previous lectures, we have already discussed all about symmetry elements, symmetry operations, definition of a group and postulates of a group. Now, next, we need to assign a molecule to its point group. A point group is an identity of a group. It's just like every student in a classroom is assigned some roll number. Similarly, every group is assigned with a point group. Now, let's talk about the definition. A point group is a collection of symmetry elements present in a molecule that obeys the mathematical rules for the formation of a group. And point groups are denoted by standard notation called Schoenfield's notations by crystallographers. I hope you understand. So what is point group? It is actually a notation which is assigned to a group, and we have already learned about the group. What is group? It is just a collection of symmetry elements that follow certain postulates. Now, these Schoenfield's notations, named after the German mathematician, is one of the two conventions commonly used to describe crystallographic point groups. This notation is used in spectroscopy. Hope you all understand what is a point group. Next, we will follow this flowchart to determine the point groups of different molecules or different groups. There are 5 steps in this flowchart. Very first, if we have to determine the point group of any molecule, we will see whether the molecule is linear or non-linear. If the molecule is linear, we will follow step 1. And next, we will see whether I symmetry operation, I means inversion symmetry operation is present or not. Now, if the molecule is linear and I is present, then the point group would be D infinite H. And secondly, if the molecule is linear but I is absent, then the point group would be C infinite V. So for linear molecules, there are 2 point groups, C infinite B and D infinite H. And it all depends upon whether I is present or I is absent. Now, if the molecule is non-linear, then we will skip this step 1 part A. Then we will look whether the molecule belongs to some higher multiple order axis, and that may be tetrahedral, octahedral or icosahedral, IH. Tetrahedral is denoted as TD, octahedral denoted as OH and icosahedral as IH. These are just the geometries of the molecule, but there is one condition that all the atoms or group of atoms which surround the central atom should be same. Let's take an example. Let's take the example of methane and chloroform. You all know both have tetrahedral geometries. The formula of methane is CH4 and that of chloroform is CHCl3. But only the difference is that in methane, all the 4 atoms, hydrogens, which surround the central atom carbon are same. Hence the point group for methane would be tetrahedral TD. But in case of chloroform, as all the atoms are not same, 3 are chlorine and the 4th one is hydrogen. So its point group could not be TD. Okay. So very first we will look whether the molecule is linear, then the point group would be C infinite V or D infinite H. Next we will look whether it is multiple high order axis. If both are absent, then we will move towards step 2. Well, in step 2, there are low symmetry axes, means no axis. Means in second step, we will consider the molecules where axes of rotation are absent. Now, there are 3 point groups in this category. These are C1, Cs and Ci. C1 is assigned to the molecular group where only identity E is present. Whereas, if along with identity sigma is present, but again there is no axis of rotation, no C, then the point group would be Cs. And if in addition to identity there is I symmetry operation, then the point group would be Ci. Okay, if the molecule or group does not belong to these categories, then we will move further. In the third step, we will consider the molecules where some Cn axis is present, and in addition to Cn, only S2n axis would be present. 2n means only even. That may be S4, that may be S6, that may be S8. Then these would be the point groups. Okay. Now, after that, we will move towards the molecules or groups where some principal axis of rotation is present. That principal axis of rotation is designated as or represented as Cn. Here again, we will divide molecules in 2 categories. First one, if any C2 axis perpendicular to principal Cn axis is absent, then if C2 axis perpendicular to Cn principal axis is absent, we will look whether sigma h is present or not. If sigma h is there, then the point group would be CNH. Means N is the principal axis. So here, in case of CNH point group, the symmetry elements which would be present is the identity. Next one is Cn, and the last one is sigma h. If sigma h is absent, then we have to look whether n sigma b's are present or not. If n sigma v's are present, then the point group would be CNV. And if there is an absence of any reflection plane, any sigma, then the point group would simply be Cn. And in the last category, we will consider the molecules where some principal axis is present, but along with the principal axis, there are n C2 axis which must be perpendicular to the principal axis. If it is present, then we will see whether sigma h is present or not. If sigma h is present, then the point group would be DNH. If sigma h is absent, then we will consider whether n sigma d's are present or not. If it is there, then the point group would be D and D. If both are absent, means only identity is present. In addition to identity, there is one principal axis and there are NC2 axes which are perpendicular to principal axis. Then the point group would be DN. Hope this flowchart would be highly helpful to you in determining the point group for any molecule. Now, let us consider some examples. Very first is the example of water molecule. As we have already discussed, there are 4 symmetry elements present in a water molecule, and these symmetry elements are identity, C2, sigma V1 and sigma V2. Now, with the help of this flowchart, as we have seen, there is a principal axis present, C2, but it is not a linear molecule, nor any multiple higher order, no low symmetry, no S2N along with Cn. So we have to move either to step 4 or step 5. Now, there is absence of any C2 axis which is perpendicular to principal axis. So we will move towards step 4 and we will see whether sigma h is present. No. Then we have to see whether n sigma v's are present. Yes. In water molecule, there is a identity, then there is a Cn axis, principal axis where n value is 2 and there are 2 sigma v's. Hence, the point group for water molecule would be C2V where n value is 2. So, hence, the point group for water molecule would be C2V. Similar is the case of ammonia. Again, in ammonia there is identity, there is a principal axis C3, okay. there is no linear molecule, nothing else, no SN axis, but no sigma H, but there are N sigma B. Again the point group would be C and V, and here the N value is 3, so the point group is C3V. Next is the square planar molecule. Now you can easily see in square planar molecule, these are the various symmetry operations we have already discussed in previous lectures. Now there is a principal axis C4, and in addition to principal axis there are 4 C2, 2 C2 dash and 2 C2 double dash, and these C2s are perpendicular to principal axis C4. So we will move towards step 5. Okay, next we will see whether sigma H is present. Yes, sigma H is present in a square planar molecule. Hence, the point group for a square planar molecule is DNH, and value is 4. Hence, the point group for square planar molecule is D4H. Now, methane is a special case. Okay, higher order axis. Again, all the 4 ligands surrounding the central atom are same. Hence, the point group would be tetrahedral TD. Next is the case where the point group would be octahedral OH. Next, there are some more examples of point groups. Very first, linear point groups. As we have already discussed, the linear point groups further depend upon the presence or absence of I. If the molecule is linear and I is absent, then the point group would be C infinite B, for example HCN. And if the molecule is linear and I is present, then the point group would be D infinite H, for example ethyne molecule, and there is another example, that is carbon dioxide molecule. Then there are some low symmetry point groups. Okay, we have already discussed, there are 3 low symmetry point groups, C1, CS, Ci. C1 where only and only one symmetry element identity is present. Here the example is substituted methane, and all the 4 substituents around carbon should be different one. Next is the CS, where in addition to identity there would be the presence of sigma H, which means molecule should be planar. Here the example is substituted ethene, and again all the 4 substituents should be different. Next one is Ci. Ci means in addition to identity only and only another symmetry element I is present, and here the example is substituted ethane, it's a trans-ethane, where 2 hydrogens are substituted by fluorine and chlorine in trans positions. Next are D point groups. Here are the examples of D point groups. Well, first one is the DN. DN means in addition to, in every D case, there must be the presence of NC2 axis which are perpendicular to principal CN axis. So first example is the D3 example. So here the principal axis would be C3, but there must be 3 C2 that are perpendicular to the principal axis C3. So the example is tris ethylene diamine cobalt 2 positive. Okay. Next one is the DNH point group. Again, DNH means there must be some principal axis C3. Okay. Next to C3 there is a NC2 axis must be perpendicular to this principal axis, and there must be the presence of sigma H. Here the example is BF3, which is a planar molecule and satisfy all these conditions. Next is the DND, where in addition to identity there must be C2, there must be perpendicular C2 axis perpendicular to principal axis, and there must be the presence of sigma D and absence of sigma H. Here the example is alene molecule. Okay, next one are the S point group. Now, we have already studied in S point group, in addition to principal axis, there must be only identity and one another symmetry operation, that is S2N. Now, the principal axis C2, then S must be S4. Here the example is cobalt 4 CP4, where CP is the cyclopentadienyl ring. Here are the examples of all the point groups with their symmetry elements, as well as some examples. As we have already done with C1, it is CF, Cl, Br, H. Okay, C infinite B means linear molecule. That is dicarbon monoxide or HCl, where I is absent. Here are some more examples. And in the end, we will discuss some important questions related to point group topic from net or gate point of view. Well, very first question here is, which two species belong to the same point group? Wow, first option is xenon F2 and OF2. Now, here the point group should not be same. Why? Because xenon F2 is a planar molecule, whereas OF2 is a bent molecule, as there are two lone pairs on oxygen atom. Next example is H2 and CO2. Again, the point group should not be same. Why? Because water is a bent molecule, whereas CO2 is a linear molecule. Yes, here the answer is C. Why? Because both H2S as well as OF2 have bent geometry, where sulfur and oxygen belong to same group having same number of valence electrons and singly bonded with in H2S with hydrogen and in OF2 with fluorine. In the next case, again the point group should not be same, because here nitrogen is surrounded by two oxygen and there is no lone pair on nitrogen, whereas in this case, in addition to oxygen, there would be one lone pair on nitrogen. So the only and only the case where the geometry is same is third one case. Hence, C is the correct answer of this question. Okay, next one. Which of the following belongs to C3V point group? Okay, as we have already discussed, in this case, now SO3 is a planar molecule, okay, where sulfur is bonded to 3 oxygen by double bonds and there is no lone pair on sulfur. Again, the geometry of BBr3 is same, it's a planar molecule. AlCl3 is a planar molecule, but ammonia is not a planar molecule. Hence, again the result of this question is ammonia, and we have already discussed in this lecture that ammonia belongs to C3V point group. Now, in next question, which molecule does not have tetrahedral symmetry? Well, in this case, for its molecule to have TD symmetry, it is a special case. There must be the presence of tetrahedral geometry, and along with that, all the 4 ligands should be same. Now, first, Si4 has a tetrahedral geometry, so it belongs to TD symmetry point group. P4 has tetrahedral geometry. CH4 has tetrahedral geometry, but xenon F4 has not a tetrahedral geometry. It is a square planar geometry, square planar shape. Hence, the answer is D, xenon F4. Now, next, which molecular ion has D3 symmetry? Now, for D3H symmetry, there must be the presence of C2 axis that should be planar to the, perpendicular to the principal axis. Means the main condition for D3H symmetry must be the presence of a planar molecule. Okay. Now, first one is H3O positive case. It is not a planar molecule. It is having tetrahedral geometry. Again, CHCl3 is not a planar molecule. NF3 is not a planar molecule. The only planar molecule in this case is carbonate ion, CO3 2 negative. Hence, the answer is CO3 2 negative, carbonate ion. Last one, SO2 belongs to which point group? Again, SO2 is a bent geometry, just like that of water. Okay, the only difference is here the sulfur, there is only one lone pair around sulfur. So, for a bent molecule, the point group would be C2V. So, for SO2, the point group would be C2V. Thank you.